All right, we just finished this definition of sequences and our definition of converge and diverge. So let's do another example of convergence and divergence. So example 9 says, does the sequence a sub n equals sine of n pi over 2 converge or diverge? And if it converges, what is the limit? So the first thing I would do in this situation is just evaluate a few things. So we're going to do n equals 1, n equals 2, etc. When n equals 1, I get sine of pi over 2. When n equals 2, I'm getting sine of pi. When n equals 3, I'm getting sine of 3 pi over 2. And then sine of 2 pi, etc. So I'm basically just moving my way around the unit circle. At sine of pi over 2, I'm getting a value of 1. At sine of pi, I'm here, and I'm getting a sine value of 0. And then I get negative 1, then 0, then 1, then 0, then negative 1, etc. So this could be defined as, I guess, negative 1 to the n if, oh dear, it won't even be, it's actually going to be to the n plus 2, because when n equals, no. Oh, this is even trickier than I thought. We want it to be 1 when n equals 1. And we want it to be negative 1 when n equals 3. So what I really want to do is I want to do something like n plus 1 divided by 2. And then here, and then I want to add 1 to that. So when n equals 1, I'd be getting 1 plus 1 is 2, divided by 2 is 1, plus 1 gives me a 2, and negative 1 squared would give me a positive. If I have n equals 3, I'm going to have 3 plus 1 is 4, divided by 2 is 2, plus 1 will give me an odd number, and when I do negative 1 to an odd number, I'll be getting a negative. And that's going to be our expression if n is odd. And we're going to get 0 if n is equal to an even number. So does this converge or diverge? The answer is it diverges. And it diverges in large part because it does not converge. It never settles down at either 1 or negative 1 or 0. It's always bouncing and forth between them. So our answer here is diverges because never settles down to one number. So, or you could also say it's always bouncing back and forth between different numbers. So as I mentioned before, there are a lot of parallels between limits of functions and limits of sequences. And in particular, we have this theorem that says if you have a limit as x goes to infinity for a particular function, and that same function is defining a sequence, then the limit of the sequence is going to be equal to that exact same limit. And similarly, if you happen to have a function that's going to infinity or negative infinity, then the sequence defined by that is going to diverge. It's also going to go to either infinity or negative infinity. So the sequence a sub n equals 1 over n, if I look at that as a function, f of x equals 1 over x, and I take the limit as x goes to infinity of 1 over x, that's just going to be like 1 over infinity. That's 1 divided by a huge number, which is just going to give us a limit of 0. Then that implies that our sequence a sub n converges to 0. Cosine of pi n, the absolute value of cosine of pi n, though, if I look at that function, what does that look like? So I'm going to graph it here real quick. Well, it looks like the cosine function, except anytime that I'd be going under the x-axis, that would be my normal cosine function. I'm taking the absolute value, so I'm in fact bouncing back up, right? So these dotted lines are where I would normally have my cosine function going, and because I'm taking the absolute value, I never get to that negative number. So this is what my cosine function looks like. Bing, 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 etc. And it's cosine of pi n, which means it's either stretched out or shrunk or something like that. So I don't know what exactly these entries would be. I could probably figure it out, but I don't really care that much. So this function, the limit as x goes to infinity of absolute value of cosine of pi x, that does not exist because it never settles down. But if I look at the actual sequence here, the sequence of cosine of pi n, what happens when I plug in n equals 1? I'm getting cosine of pi. And cosine of pi is, sorry, this is absolute value. I'm going to do it on the unit circle here. Cosine of pi is here, I'm getting -1. But I'm taking the absolute value of that, so I get a +1. And then when I plug in n equals 2 to this expression here, I'm getting cosine of 2 pi, which is giving me a +1. Absolute value of that is 1. And then I go 3 pi here, and I get -1. Absolute value gives me 1, etc. This sequence is always giving me a value of 1 because it's just taking these top entries at the top of each of those humps. So this does, in fact, converge. The limit as n goes to infinity of the sequence absolute value cosine of pi n, that's equal to 1. So the trick about this theorem is just because the limit of the function doesn't exist, if it's like bouncing around to things, that doesn't necessarily tell you that the sequence doesn't exist. If the limit of the function does exist, then we know that this is true for the sequence as well. And if the limit for the function does not exist because it goes to positive or negative infinity, then we know what happens with the sequence. But if it's just bouncing around, it doesn't necessarily tell us everything. Now, since these limits of functions and sequences are so closely related, we are going to do a quick review of everyone's favorite mathematical theorem that looks like hospital, but is actually pronounced l'hôpital. We're going to remember L'Hopital's rule. So suppose we have these two functions that are differentiable, and your bottom one is not going to have a derivative of 0 near a point P. Except possibly at the point P, yet that's allowed. And suppose further that the limit as x approaches that point P of your function f of x is equal to 0, and the limit as x approaches P of the g of x equals 0. That would be giving us a expression of the term 0 over 0 as we approach the point P. Or the limit as x approaches P of f of x is positive or negative infinity, and the limit as x approaches P of g of x is also, that's not what I meant to do, positive or negative infinity. So that's something of the form infinity over infinity. So these are our two indeterminate forms. Then L'Hopital's rule says the following. The limit as x approaches P of f of x over g of x is going to be equal to the limit as x approaches P of f prime of x over g prime of x. That's assuming that this second limit exists or is positive or negative infinity. In other words, L'Hopital's rule says if you have a limit and you've got a fraction that you're dealing with and you're getting 0 over 0 or infinity over infinity, you can take the derivative of the top and bottom functions and then take that limit, and it'll give you the same answer as what you would have gotten for the original one. So let's do a few examples. So as x goes to infinity, natural log of x goes to infinity. So that means natural log of x is going to be a natural log of infinity. That's also going to go to infinity. And of course, x also goes to infinity. So this is of the form infinity over infinity. So what I do to demonstrate that I'm using L'Hopital's rule is I put a little h over my equal sign. And now I say, okay, I can do L'Hopital's rule, so I'm going to take the derivative of the top and the derivative of the bottom. So I take the derivative of the top, I get 1 over natural log of x, and then I multiply by the derivative of what's inside the function there, the natural log of x, and that gives me a 1 over x. And I divide that by the derivative of x, which is just 1. And now I simplify. This is the limit as x goes to infinity of 1 over x times natural log of x. That's just going to be 1 over infinity. Both the x and the natural log of x will go to infinity. So that gives me 0. Exercise 12 and exercise 13 are ones I want you to work on your own. So go ahead and take a minute and try to work those out. Pause the video, and when you're done or you're stuck, turn on the video and I'll give you your answer. Pause. Okay, so for exercise 12, what I'm actually going to start off doing is rewriting this expression so it looks like a fraction. E to the x squared over x cubed. As x goes to infinity, both of those, the top and the bottom, are going to go to infinity. So I'm going to do L'Hopital's rule. Take the derivative of the top and the bottom. For the top, I get an e to the x squared, and then I multiply by a 2x, because I do the chain rule on that. And on the bottom, I get a 3x squared, and one of these x's will cancel out. So this ends up giving me the limit as x goes to infinity of 2e to the x squared over 3x. That is still infinity over infinity. So I'm going to do L'Hopital's rule again. And when I take the derivative of these two, I have a 2e to the x squared, chain rule on the x squared and get a 2x, and then on the bottom I just get a 3. So now our top goes to infinity and our bottom just stays at 3, so this is going to go to infinity. And exercise 13, this one's interesting because when I rewrite it, maybe I'll do this one in blue. I want to make that e to the negative x a positive exponent. So this is 1 over e to the x times x. And as x goes to infinity, this is just 1 over infinity, which gives me 0. So I don't do L'Hopital's rule at all for this one. And I think if you do L'Hopital's rule, you'll probably get the wrong answer because it was not indeterminate form in the first place. So you always need to make sure that you have the indeterminate form at the very beginning, or else you can get the wrong answer. So we also have these limit laws that mirror our limit laws for functions. So these are limit laws for sequences. So if we have these two convergent sequences, a sub n converging to L1, b sub n converging to L2, and c is just some constant, then if I take the limit of adding the two sequences together, what I'm going to get is the sum of the limits. The same thing holds for subtraction. If I take each of my entries in my sequence a sub n, and I multiply it by that constant, I'm going to end up getting a limit that's just c times the limit that I had for the original function. And one way to think about that is that if you take the limit as n goes to infinity of a constant function, you're just getting that same constant. You're just getting that same number back. So it's not going to change anything. Similarly, if I've got these two convergent sequences, and then I want the sequence where I'm multiplying the two together, that's going to give me just the product of the two limits. And this is also true for division as long as your denominator is not equal to 0, because that ruins everything. And last of all, if you have a convergent sequence and then you try to raise that sequence to a particular power, and this p is a fixed number. It would be like if I had a convergent sequence and then I said, now I'm going to square all of those terms. What would I get for that sequence? What you get is just the limit for the sequence a sub n raised to that power. So kind of exactly what you would expect. And notice here it says that the a sub n has to be greater than 0. That means all of the terms in the sequence have to be positive. And the trick about this is that you can actually have, if you're raising your p to say a positive power, say, an even power, you could be taking something that had, say, negative numbers, and that would then be turning into positive numbers when you square them. That can throw things off. So this is why we only want to keep it with those positive entries in our sequence.